And welcome back. As we continue our cosmic journey, we are going to now take a closer look at the giant planets that are in the outer portion of our solar system. So let's start first by looking at a few basic characteristics of these giant worlds. The giant planets, of course, are very far from our own sun. Jupiter orbits at 5 AU, or 5 times the distance between the sun and Earth, and takes nearly 12 years to orbit the sun. Saturn orbits at 10 AU, or 10 times the distance between Earth and the Sun, and takes nearly 30 years to complete one orbit. Uranus orbits at 19 AU with a period of 84 years, while Neptune at 30 AU requires 165 years for each circuit of the Sun. Now you'll notice these are quite long timescales, and because they are very long, it actually makes it very difficult for us here on Earth to study seasonal changes on the outer planets. Jupiter and Saturn have many similarities in composition and internal structure, although Jupiter is nearly 4 times as massive. Uranus and Neptune are smaller and different composition and internal structure. So let's go ahead and start going a little further by looking at the mass and density of the giants. Jupiter has enough mass that you could make 318 Earths, and its diameter is about 11 times that of Earth. So you could put 11 Earths side by side, and that would be the diameter of Jupiter. Now, Jupiter's average density is 1.3 grams per centimeter cubed. Just for reference, the density of water is considered to be 1.0 grams per centimeter cubed. So that's, of course, giving you just some context there. And you can see with Jupiter, that density is much lower than that of any of the terrestrial planets. Earth, Venus, Mars, and Mercury all have a much higher density rating on them. Saturn's mass is 95 times that of Earth, and its average density is only 0.7 grams per centimeter cubed, which is the lowest of any planet. In fact, if you could find a way to do it, Saturn has a much lower density of water, and if you were to place Saturn in a big enough bowl of water, theoretically it could float, because again, it's lower than the actual density of what water is. Now, Uranus and Neptune each have a mass that's about 15 times that of Earth, and hence are only about 5 times as massive as Jupiter. Now, their densities are 1.3 grams per centimeter cubed and 1.6 grams per centimeter cubed respectively, and you notice that these, of course, are much higher than Saturn, which makes Saturn kind of unusual in this aspect. Now, we start talking about the appearance of the giants. When we look at the planets, we see only their atmospheres. Remember, they don't really have a surface as we would expect on things such as our inner planets. And these, again, are primarily because they're composed of hydrogen and helium gas. Now, the uppermost clouds of Jupiter and Saturn, which is the part we see when we're looking down at these planets from above, are composed of ammonia crystals. On Neptune, we'll find that the upper clouds are actually, though, made of methane. And if you're on Uranus, well, we don't really see an obvious cloud layer at all, but only kind of a deep and featureless haze. Now, when we start looking at the rotation of them, again, this is going to lend us some more interesting things about the giants. We measure Jupiter's rotation through periodic variations in radio waves that come from Jupiter, which are controlled by its magnetic field. Since the magnetic field originates deep within inside the planet, it shares the rotation of the interior. Therefore, we can start measuring things, such as the rotation period in this way as 9 hours and 56 minutes, which gives Jupiter the shortest day of any planet in our solar system. So about every 10 hours, Jupiter has spun from day to night and back. So that is a very fast cycle there if you think about it. In the same way, though, we can measure the underlying rotation period of Saturn to be 10 hours and 40 minutes. And again, you can see Saturn is also very, very fast here. We're looking at a little under 11 hours here for Saturn compared to Earth's 24. Now, Uranus and Neptune have slightly longer rotation periods, about 17 hours. And again, we've also determined this from the rotation of their magnetic fields. Now, there are, of course, seasons on the giants, but how these look depend based on which planet we're examining. So, what do those seasons actually look like? Well, the spin axis of Jupiter is tilted only by about 3 degrees. So, with Jupiter, there's really not any seasons to speak of, because at 3 degrees, you really don't get as much variance as you would with something like, remember, Earth is a lot larger, and so that's why we have such pronounced seasons. So if we look at something larger like Saturn, it does have seasons, since its spin axis is inclined at 27 degrees to the perpendicular of its orbit. Neptune tilts at 29, and there experiences similar seasons to Saturn, only a little bit more slowly. Now, the strangest seasons of all are actually on Uranus, which has a spin axis tilted by 98 degrees with respect to the north direction. Practically speaking, we can say that Uranus orbits on its side, and its ring and moon system follow along, orbiting along Uranus's equator, which is why if you ever see any diagrams of Uranus with its ring system, well, it's like you'll see with Saturn's where they kind of run more of a left or right direction. Uranus's will kind of run more up and down, again, because it kind of sits more on its side here. So let's talk about that strange tilt of Uranus just for a second here. We don't know what caused Uranus to be tipped over like that. Why is it, the lazy planet that wants to sit on its side and not get out of bed? We don't really know, but the one theory, or one possibility, is that early on, Uranus had a collision with a large planetary body when our solar system was first forming. And when that collision happened, it tilted Uranus to a very severe degree. Similar to kind of like with Earth, why do we have such a large axial tilt? Well, part of the reason is we think that could have also been from a planetary collision, which, as we discussed previously, was something that very also likely formed our moon. Now, whatever the cause was for Uranus, this unusual tilt creates dramatic seasons. When Voyager 2 arrived at Uranus, its south pole was facing directly into the sun. Now, the southern hemisphere at that time was experiencing a 21-year sunlit summer, while during that same period, the northern hemisphere was plunged into total darkness. For the next 21-year season, the sun shines at Uranus's equator, and both hemispheres go through cycles of light and dark as the planet rotates. So let's talk a little bit about some of the internal structures of the Jovian planets here. Jupiter and Saturn are composed primarily of hydrogen and helium, but Uranus and Neptune consist in large part compounds of hydrogen, nitrogen, and oxygen. Now, the deep internal structures of these two planets are very difficult to predict because, again, they're so massive, it's very hard to really probe deeper down. This is mainly because they're so big and that the hydrogen and helium in their centers are tremendously compressed and behave in ways that the same gases on Earth would never behave that way. So if I were to look at hydrogen and helium, they're not going to behave exactly the same. If we look again at this picture, you can see even this breakdown. We have what's called molecular hydrogen, metallic hydrogen, then ice and rock. Molecular hydrogen, metallic hydrogen, ice and rock. Again, you can see kind of some of the things here. But with Neptune and Uranus, of course, you do not see the metallic hydrogen. You simply see molecular hydrogen, ice, and rock. So with that composition, at the pressures inside the giant planets, familiar materials can take on strange forms. A few thousand kilometers below the visible clouds of Jupiter and Saturn, pressures become so great that the hydrogen changes from a gaseous to a liquid state. Still deeper, this liquid hydrogen is further compressed and begins to almost act like a metal, something that it never does on Earth. On Jupiter, the greater part of the interior is liquid metallic hydrogen. And because Saturn is less massive, it only has a small volume of metallic hydrogen, but most of its interior is liquid. Now, Uranus and Neptune are too small to reach the same internal pressures sufficient to liquefy hydrogen, but they, of course, still have their own unique properties. Now, if we start examining the structure of our gas giants, each of these planets has a core composed of heavier materials, such as demonstrated by detailed analysis of their gravitational fields. And we'll see this also with our ice giants as well. Presumably these cores that are in there are the original rock and ice bodies that formed before the captured gas from the surrounding nebula. Now, it appears that all four of our giants have similar cores of rock and ice. On Jupiter and Saturn, the cores constitute only a few percent of the total mass. However, most of the mass of Uranus and Neptune resides in these cores, demonstrating that the two outer planets were unable to attract massive quantities of hydrogen and helium when they were first forming. Now, of course, we can't talk about our planets without discussing their internal heat sources. Because of the large size, all the giant planets were strongly heated during their formation by the collapse of the surrounding material onto their cores. Now, some of this primordial heat can remain inside of a planet, especially because they are so large. In addition, it's possible for giant, largely gaseous planets to generate heat after formation by slowly contracting. Now, the effect of these internal energy sources is to raise the temperatures in the interiors and atmospheres of the planets higher than we would expect from the heating effect of the sun alone. So, if we look at those differing heat sources, what are they? Well, Jupiter has the largest heat source, being partially from the sun and partially internal. Most of the internal energy of Jupiter is primordial heat, which is simply heat that's left over from the formation of the planet 4.5 billion years ago. Saturn has an internal energy source about half as large as that of Jupiter. Much of Saturn's energy comes from the differentiation of helium and hydrogen. And if you remember, differentiation is simply just the separation of those layers, much as how we see the inner planets, how they differentiate it into their different layers. Now, Neptune has a small internal energy source, while Uranus does not emit a measurable amount of internal heat. And because of that, both worlds result in nearly the same atmospheric temperature. So let's talk about the magnetic fields now of those same planets, because obviously if we have a core, we can generate hopefully some kind of magnetic field. Each of the giant planets has a strong magnetic field generated by electric currents in its rapidly spinning interior. Associated with magnetic fields, of course, are the planet's magnetospheres, which are regions around the planet within which the planet's own magnetic field dominates over the general interplanetary magnetic field. Now, the magnetospheres of these planets are their largest features, extending millions of kilometers in space. Inside each magnetosphere, charged particles spiral around in the magnetic field. As a result, they can be accelerated to high energies, and these charged particles can come from the sun or from the neighborhood of the planet itself.